Greetings, Dr. Dan with Optimal Optics, here to introduce Unit 7P, Refraction of Paraxial Rays at a Spherical Surface word problems. So this assumes you've already viewed Unit 7. Question 1. A lens focuses light toward a point 10 centimeters beyond a concave surface separating water, n equals 1.33, from glass, n prime equals 1.55. The radius of the surface is 20 centimeters. Find the point where the refracted ray crosses the optical axis and round your answer to the nearest tenth. So already I've drawn a diagram. The locations of F prime, C, and F are approximations, and what that means is when you draw the diagram, you may find your image location does not exactly match the location that you find from your calculation after plugging into the formula, and that's fine. The important thing is the diagram will tell you which side of the surface the image is on. If it's erect, if it's inverted, you get valuable information from the diagram, but just be aware it may not precisely match up with what you calculate. So we have a virtual object on the right side of the surface created by this lens. We have n equals 1.33 and n prime equals 1.55. We're given that the radius is 20, therefore r is equal to negative 20, AC right to left. We're given the object is 10 centimeters from the vertex. It's a positive number. U equals AM, positive 10, and we're looking for U prime. So we're going to plug into the formula that we learned in Unit 7. N prime over U prime equals N over U plus N prime minus N over R. We'll plug in what we know. And let's choose 20 as our common denominator for the right side of the equation. And let's get rid of the parentheses. And we find that the right side of the equation equals 2.44 over 20. Now we'll cross multiply. And we find that U prime equals 12.7 centimeters. So it's inside the glass. It's on the right side of the surface, a positive number, AM prime. So let's see what happens when we draw it out. We'll place our object at M. We'll draw our ray parallel to the optical axis at the height of M. We'll have it refract through F prime. And then we'll send a ray through the center from the top of the object. And as we extend our rays back, we see that they meet right around there, coincidentally near F. Question 2, the radius of a concave refracting surface is 20 centimeters. A virtual image of a real object is formed at a distance of 40 centimeters from the vertex. The distance from the object to the image is 60 centimeters. The first medium is air. Find the index of the second medium. So if you recall from Unit 7, a real object in front of a concave refracting surface forms a virtual image, assuming that the index on the left is less than the index on the right. So the radius is negative 20, A to C right to left. The image distance U prime is negative 40, AM prime right to left. And since the object is 60 centimeters from the image, the object distance is negative 100 AM right to left. So we'll plug into our formula what we know. Now let's choose 200 as our lowest common denominator. Now we'll get rid of the parentheses by distributing negative 10 over what's inside. Combine the right side into one fraction. We can cancel out the 200 in each denominator. And we find that n prime equals 1.6. Question 3, find the positions of the primary and secondary focal points of a concave spherical surface separating air from a medium of index 1.6, having found that the image of a luminous point 30 centimeters in front of the surface is midway between the luminous point and the surface, and round your answer to the nearest hundredth. So we're given n is 1 and n prime is 1.6. We're given that the object distance is 30. But because it's measured from A to M, it's a negative 30. And the image distance is halfway between, it says, so U prime is negative 15, measured from A to M prime. So now we're going to use the formula n prime over U prime equals n over U plus n over F. Plug in what we know. We'll use 30 as our common denominator, and bring the fraction on the right over to the left side. That's minus 2.2 over 30 equals 1 over F. Cross multiply. And we find that F equals negative 13.64 centimeters. F, the focal length, is measured from F to A, negative direction. So that makes sense. And n over F is equal to negative n prime over F prime being the secondary focal point. So again, we just plug in and we solve for F prime. And we find that F prime equals 21.82 centimeters, and that's the distance from F prime to A. Question 4, a beam of parallel rays passing through water, n equals 1.3, is refracted at a concave surface into glass, n prime equals 1.5. If the radius of the surface is 20 centimeters, where will the light appear to be focused? So there's a parallel ray parallel to the optical axis. It will be refracted away from the normal and appear to be coming from F prime. So we have the radius is 20 because it's measured from A to C, a right to left direction, that's negative 20. N is 1.3, n prime is 1.5. We know that n prime minus n over r equals minus n prime over f prime. That's the formula we'll use. We plug in to find what f prime equals. Cross multiply. And we find that f prime equals 150 centimeters. And that's the distance from f prime to A, a positive number. Question 5, a small air bubble is embedded in a glass sphere at a distance of 5.98 centimeters from the nearest point on the surface. What is the apparent depth of the bubble if the radius of the sphere is 7.03 centimeters and the index of refraction of the glass is 1.42? Round your answer to the nearest hundredth. So we have our diagram already drawn. We know n equals 1.42 and n prime equals 1. Now here's an example of a index on the left side of the surface being greater than the index on the right side. And therefore, f prime is on the right side of this concave surface rather than where we usually find it on the left side when the relative indexes are reversed. So we've drawn our line through the normal, and the parallel ray will be bent away from the normal to F prime. This is why F prime is on the right side. Let's get rid of the normal. So we're given that the object distance is 5.98. U equals negative 5.98, measured from A to M, right to left. We're given the radius is 7.03, and it's equal to negative 7.03, again measured from A to C, right to left, and we're looking for U prime. So again, we plug it into our familiar formula, N prime over U prime equals N over U plus N prime minus N over R. And now we'll have to use a calculator. So we find these decimals. And we find that U prime equals negative 5.62 centimeters. So we expect it to be right around there, a little closer to the surface than the object is. And if we extend our ray to the focal point and send a ray to the center, that's just about where the image is formed, right there. Question 6, a real object 1 centimeter high is placed 12 centimeters from a convex spherical refracting surface of radius 30 centimeters, which separates air from glass. N prime equals 1.5. Find the position and size of the image. I bet you never thought we'd get to a convex surface. Here we are. N equals 1. N prime equals 1.5. Object distance U equals negative 12 from A to M. The radius going from A to C is a positive 30, going from left to right, and we are looking for U prime. And eventually we'll find the size of the image with the formula Y prime over Y equals the magnification. So first we'll plug into our familiar formula. Solving for U prime. Okay, let's make 60 our common denominator. So we have negative 4U prime equals 90, and U prime equals negative 22.5 centimeters. That's the distance from A to M prime, the image position. So it'll be further to the left of the surface. That makes it a virtual image. And we can draw it out by sending our parallel light ray through F prime, extending it back, sending a ray to the center, and we find those two rays intersect right around there. So it's virtual. Now the formula for magnification is Y prime over Y equals N over N prime, U prime over U. And we plug in and we find it equals 1.25. A positive number means it's erect. We multiply that times the object size, which is 1 centimeter, and we find the image is 1.25 centimeters high. Okay, for you Finding Nemo fans, here's a problem about Dory the fish, who is swimming in an aquarium where a flat sheet of glass separates her from the people on the other side. A small defect in the glass produces a spherical refracting surface bulging toward the air with a radius of curvature of 0.75 centimeters. Dory views the 25 centimeter high head of someone standing 9 centimeters from the glass through that defect, and she freaks out. Assuming that the water has an index of refraction of 4/3, calculate the location, size, and nature of the image to determine why Dory got so confused. So the radius of this convex defect is AC, a positive number, 0.75. The person standing on the other side of the glass is 9 centimeters away. AM, that's a negative number, -9. And we're finding U prime. So the formula again is n prime over u prime equals n over u plus n prime minus n over r. We'll plug in what we know. And since everything's in fractions, let's make r, instead of 0.75, let's make it 3/4. Okay, we'll make the equation look a little prettier. All those equations on the right side, all those fractions on the right side, reduce to 4/9. So the right side of the equation becomes 1/3. Now we'll cross multiply. 3u prime equals 12. U prime equals 4 centimeters. Now we'll calculate the image size with the magnification formula. We'll plug in what we know. Y prime will be the image size. So the magnification is -1/3, and we find when we cross multiply, 3y prime equals -25, and y prime equals -8 1/3 centimeters. So what does all this mean? It means that when Dory is swimming in the water, looking through that defect, there's a disembodied, upside down, shrunken head in front of her. And that, I think, would scare anybody, not only Dory the fish. Yeah, let's draw it out now. So our parallel ray goes through F prime, and our ray through the center meets that ray right there. So this is where the image of the head would be, upside down and smaller, appearing to float right in front of Dory. No, this is not a condom. This is Dory the fish, freaking out, seeing a shrunken, upside-down head in front of her. If she were a sole fish sitting on a perch, she might say, "Holy mackerel."